Let's look at how we can use PSPICE to analyze the pulse response of an RC circuit. So in PSPICE, they have as one of the input voltage sources a pulse source. Once you enter it into your schematic diagram, you'll see this little pulse on there. What you can set up for the pulse response, this should actually say V2. So that's an editing error. So let's just put a 2 here. In this case, what we'll be using in this example is I've set up V1 to be equal to 0 volts, and it's going to pulse, it's going to rise to V2, which I've set it to be 9 volts. The delay, the amount of time it takes for this input source to rise, I just have it 1 nanosecond and fall in 1 nanosecond. This looks like it actually takes a lot longer to fall than to rise. So, but this, I have what I'm going to set up as a pulse width. That's the pulse width. The pulse width is the period of time that the pulse is high at the high voltage. I have that set up at 10 milliseconds and the period set up at 15 milliseconds. So we have a shorter low pulse than we have a high pulse. So you can do this in PSPICE, and we'll do this. And set up that source. If in this example, what I set up is a 1 microfarad capacitor in series with a 1 kilo ohm resistor. So the time constant then, our RC time constant, tau is equal to RC is just equal to 10 to the negative 6 times 10 cubed. So that's equal to 10 to the negative 3 seconds, or it's equal to 1 millisecond. So our time constant here is much less than this pulse width high. So this is, if this looks like it's about 2 milliseconds. So one time constant is right here. So after one time constant, we've risen to about 63% of our final value. So by 5 time constants, we're at we are at about 99% of our final value. So we're able to not only rise, but stay at our risen value before then we have to fall again. And we're falling, we have 5 time constants there. So we have plenty of time to rise and just enough time to fall before it rises again. So that's an example of how we could, the response of that voltage across the capacitor, that could be the voltage across the capacitor or the current through the circuit. But it says it's the capacitor voltage in this circuit. If, however, I set up the pulse so that it was only high for less than 1 millisecond, this looks like this is 2 milliseconds. It looks like it's only high for 0.5 milliseconds here, and that's what it says up here, right? So we're only high for 0.5 milliseconds. We still have that period of 15 milliseconds. Well, we're just not able to rise. That's half of a time constant, so we don't even get halfway up to our final value. We just get to basically we'll get to our 9 volts times 1 minus e to the negative t over tau. So we got 0.5 over 1. So e to the negative 0.5. So we don't rise very far, and we come back down. So it looks we really can't exercise the circuit that has a 1 millisecond time constant with an input pulse of 0.5 milliseconds, regardless of what the period is. So these are different examples comparing the time constant to the pulse width, and not only the pulse width, but the t minus the pulse width, so the period of time that the pulse is high and the period of time that the pulse is low. So if we step through these examples, this worked very well because the time constant was much less than the pulse width. It was also much less than t minus the pulse width, or the period of time that the pulse was low. If we have that our time constant is much less than the pulse width, but it's much greater than the time that the pulse is low, or t minus the pulse width, then we rise, but we're not able to fall. So it looks like it's just sitting up here at around 9 volts. It drops a little bit, but we just sit up there at 9 volts. If we have that the time constant is much greater than the pulse width, then we're not able to rise, but we're able to fall. This was the example we saw earlier. But however, if the time constant's much greater than the pulse width, and it's much greater than pulse high and pulse low, but the period of time that it's high, the pulse is high as compared to its low, then we'll just sort of step our way up over time, and it'll basically just look like noise sitting up there. And not at 9 volts, right? We're still only up there around 4.5 volts. So this is how we can exercise our RC circuit with PSPICE to see these various examples. We're also working the lab on such a lab. And that's it for this video. Another video will analyze some more circuits.